In this lesson, I want to briefly touch on some of the main topics from Unit 6 on exponential equations. We looked kind of at some basic exponent properties and writing, graphing exponential equations. This is just a brief overview of some of the topics that are going to be on the test. So these first few are working with exponent properties. As you can see on the right here, I went and copied some of the stuff from our notes, and I'm going to kind of reference that as I work through this process here. Note that it's only the exponent properties from the first page, so it doesn't include the properties we use when we divide. However, what I'm going to do first is note that this little dot here in between the two bases means that I'm multiplying, right? And so what I'm checking to see is, do I have the same base? Remember, the base is the thing on the bottom, and then the little power is the exponent, right? And so it does look like I do indeed have the same base, right? I have a base of 4. And so what my rule tells me right over here, this very first rule, is that when I have the same base and I'm multiplying those bases, I'm going to add the powers, right? You can see n plus m. That's kind of my shortcut. So that's what I'm going to do over here. I'm going to maintain the same base, so I still have a base of 4. But what I can do is add the powers, the 2 and the 3. And 2 plus 3 gets me 5. So I'm going to write that as 4 to the power of 5. And this is how Big Ideas wants you to write your answers. As you can see, the instructions here says write your answer as a power. But if you were doing this on paper, it would be nice to then expand that all the way out by typing in your calculator 4, then the little caret button, and the 5 to get 4 to the power of 5. Or you can also remember that that means 4 multiplied 5 times. Okay, but that would take a while to multiply out, so you just want to do 4 to the power of 5. Which equals 1024, okay? But as far as Big Ideas is concerned and the instructions for that question, you should leave it like that, 4 to the power of 5. Now this one right here looks a little different, because you can see I don't have two bases, right? There's not another a sitting out there. So what this guy is actually called is a power to a power. I like to call them superpowers. And if I scroll and look over here, when I have a power to a power, what I'm supposed to do is multiply the exponents. So what I'm going to do is maintain, once again, that base of a. He doesn't go anywhere. And then I'm going to multiply my two powers. So I'm going to do 5 times 5, which, as you remember, 5 times 5 is going to get me 25. So I have a to the power of 25. And there's nothing else we can do with that, right? I could write a out 25 times, but that would be kind of redundant. Next one here. Again, simplifying the expression. This time it's a little different. This bar here, remember, means to divide. So once again, I'm going to look for the same base. I see I have a base of 6 and a base of 6. And so I don't have it copied over here, so I can't exactly scroll over. But what I do know is that when I divide things with the same base, I can subtract the powers. Is kind of my shortcut. You could also list it all the way out, right? Write 10 sixes on the top. And think of it this way. If there were 10 sixes on the top and 4 sixes on the bottom, how many would I end up having left? Or 10 minus 4. And you know that you'd end up having 6 sixes left. Kind of a tongue twister there. You can do 10 minus 4 as our shortcut. Or again, like I said, think 10 on the top, 4 on the bottom. When I cancel them out, because it's all multiplication, right? So I can cancel. I end up with just, not 4, sorry. I end up with 6 left. And they're all in the top, right? So it's a positive power, 6 to the power of 6. We're not going to worry about negative powers on this particular test. And I'm going to leave my answer, again, written like that, because it needs to be written as a power. Same deal here, right? Once again, I see I'm dividing, and I have the same base, larger base, right? But it's still 64. Or sorry, they're both 64. And so what I can do is subtract the powers. So I can do 64 to the power of 4 minus 3. 4 minus 3 equals 1. So I can say 64 to the power of 1. Which what's 64, not multiplied by anything, multiplied by 1 basically. 64 is equal to 64. And that would be your final answer. There's nothing more you can do with that. Once again, simplify this expression. I can see that I only have one base, right, a base of 5, and I have power to a power. Remember, power to a power means I multiply the exponents. So I'm going to do 5 to the 4 times 3. And that's going to get me 5 to the power of 12. That's my final answer. It's in simplest form. Same deal here. I see that I have a base of b, And a power to a power, when I have a power to a power, I need to multiply the exponents. So I'm going to multiply 12 and 3. And when I do that, I get 36. So b to the power of 36. And that's my answer there. Next, we're going to take a look at exponential growth and exponential decay. Okay, and I'm going to use some of the notes that I have right up over here to help me answer these questions. So this first question here asks me to determine whether the function represents exponential growth or exponential decay. Then I need to identify the percent rate of change. But let's start with the first part. If I look up here, exponential growth is determined by my b value being greater than 1. I should actually add this to the notes too. And exponential decay is it's smaller than 1. It still has to be bigger than 0. It's one of our rules. But just think of it, is it bigger than 1 or smaller than 1? And in order to figure out which one, I should have included this. Sorry, it's further down in my presentation. Y equals a times b to the power of x. That's like our common form of the exponential function. Sometimes often actually, we like to write it like this. And instead of using the dot for multiplication, we just use a little parentheses. So b is the number that has the power on it, basically, is what we're looking for. It's usually in parentheses. It's definitely the one that has the power attached to it. So I've got two numbers here. That 30 is the a, which means the 0.95 is the b, because it has the power attached to it, that power of t, okay? What I'm trying to figure out is, does that 0.95 represent growth or decay? Well, I believe that it's true that 0.95 is smaller than 1, which would mean, according to my notes up here, that it's exponential decay. Okay, so that's would be what I would, oh, I guess I deleted the answer boxes on this one. But we would say it's exponential decay. On big ideas, there will be a drop down for you to select there. Now identify the percent rate of change. That's the second part. In order to do that, I need to use these formulas that I have here. So percent rate of change, or like the percent of growth or percent of decay. So you have to decide if you're working with a growth function or a decay function, because that changes what you're going to do, all right? And since we already identified that it's a decay function, since b is smaller than 1, in fact, in between 0 and 1, what we're going to do is take 1, subtract b, and then multiply by 100, right? That last part, that multiplying by 100, is just converting to a percent. So you don't need to worry about that if you're really comfortable with converting to percents. So I'm going to do 1 minus 0.95, and then at the very end, I'm going to multiply that by 100, okay? And be very careful when you type that in your calculator. Either use parentheses or do the 1 minus 0.95 part first. That would get you 0.05. And then when we multiply that by 100, it just moves the decimal place 2 to the right, which gets us in the end 5, or 5%. So the rate of change is 5%. It means it's decreasing by 5% every year, or depending on what t exactly represents, but I assume it's a year. Once again here, we have to determine if the function represents exponential growth or exponential decay. As a reminder, we're looking here at our b value to determine that, and I would like to say that 1.08 is bigger than 1, which means that it represents exponential growth, right, since b is bigger than 1. Now we have to find the percent rate of change, okay, and we're going to do that using the other formula that's up here, right, that one that had the green arrow pointing to. B minus 1 times 100. See how that's a little bit different than the previous one? So now instead of starting with 1, I'm going to start with b, subtract 1 from b, and then again that multiplying by 100 part, just simply to convert it to a percent. When I do 1.08 minus 1, I get 0.08, right? And then I multiply that by 100, which means I move that decimal place 2 to the right, and what that gets me in the end is 8. I add my little percent sign, so 8%, which means each year it's growing by 8%. Let's go ahead and circle that. So exponential growth and 8%. I'm going to go ahead and skip this one because I've done quite a few like that, but you can see just really quickly, honestly, that it's growth because that b their value there is bigger than 1. And then I know 0.06, and then I convert it to a percent, which would give me 6%. So pretty easy, right? I know I said I'd skip it, but you can kind of run through these really quickly. Once you've done quite a few, you'll be able to really quickly determine the rate of change without actually doing too much of the math. Next is to be able to find the exponential function given the table. So we have to figure out what the a value is and what the b value is, right? One little hint that I have done here at the bottom is to take the y value and divide it by the y value before it. And you'll kind of notice on this review, I'm not going to talk about finding from a graph. That's something else that we'll tackle in maybe another video. But anyway, what I have to do is pick a y value, any y value in the table really. So let's just say we'll start here with this y value of 10. Okay, and I have to divide by the one that comes before it. This is really easy to see in a table because as long as these are going in order by 1, right, the one that comes before it would just be that one right there. That makes sense, right? Because here the x value is 1. What comes before 1? Well, the number 0 comes before 1. So I'm going to do what's in the orange arrow divided by what's pointing to the blue arrow, right? The y value divided by the one that comes before it. And you'll notice no matter which one I choose to start with, say I choose 50 to start with, let me color code that, 50 to start with, and then 10, you're going to kind of notice here that you'll end up getting the same result. So let's try that. 10 divided by 2 is 5. So b value of 5. And guess what? 50, oh, not divided by 2, sorry. That'd be 50 divided by 10 is also 5. Miraculous, right? So wherever you start, you divide by the previous one, y value, and you get your b value, which is your multiplier, is kind of what we call it. Okay, so we know that my b value, or my multiplier, is 5 in that case. I'm going to go ahead and erase that there. And no, we could have started really with any of them, but even if I did 2 divided by 2 over 5, that would also get me 5. Okay, so now that we have our multiplier, the last thing we need to find is our a value. I'm going to kind of run down here. Note that right here we noted that the a value is the starting value, or the starting amount, which is where x equals 0, because it's the y-intercept. So what I do is I look at my table and I ask myself, oh, where in all of these values is x equal to 0? Well, how about right there? That looks like x equal to 0. And what's the y value associated with it? In this case, it is 2. So that means my y-intercept is 2, so my a value is 2. Finally, all I have to do is put that sucker into the exponential form, which is down there, y equals ab to the x. Boom. If that's the most comfortable way for you to do it, that's totally fine if you write it like that. And I actually like to make a red. So y equals a times, little dot for times, please don't use the x, b to the power of x. Another way to write that, just for clarity's sake, is y equals a parenthesis b, close parenthesis, to the power of x. I'm going to do that with this table right here really fast. Oh, sorry, one other thing really quickly to look at is note that if you take a look at the table here, you can see that your y values are increasing, right? Which means that it's a growth function. You can tell just by looking at them. As x increases, y increases also. Okay, which means that my b value, or the multiplier, should be bigger than 1. Is 5 bigger than 1? Yes, it sure is. When you're doing this with graphs, a way to check is, hey, if it looks like that, it's growth. If it looks like that, it's decay. So it should be bigger than 1 and or smaller than 1. So once again, I'm going to use this formula here, y value divided by the y value that comes before it, in order to figure out what my multiplier is. So I'm going to pick 4 and divide by the y value that comes before it. This is where it's really helpful if you've got good fraction skills, because watch this, 4 divided by 24. If I type that in my calculator, I'm going to get a decimal, which is okay but not super useful, especially this particular decimal. It's a repeating decimal. So what I want you to do instead, if you are using your calculators, most of you have this button that looks like this, ABC. And so use that button to type that in as if it's a fraction, and your calculator will actually simplify it for you. What I'm going to do is divide the top and bottom of my fraction by 4, because I know that's going to get me 1 over 6, which is my b value, or my multiplier. And I would have gotten the same result if I started here and divided by here, and so on and so forth. Next is to find a. Remember, we know a where x equals 0, because that's our y-intercept. There's where x equals 0, and the y value there is 4. So be careful not to just say, oh, it's 0, right? Because we want to know what the y value is at that point. and the y value is 4. Note here I said f of x, but it's just function notation. Don't let it freak you out. We talked about that all chapter 3. So f of x, or a function containing the variable x, is 4. And I'm going to do it the fancy way this time. Parenthesis b, my multiplier. So a, parenthesis b, all to the power of x. And I know I have to use the variable x because that's what it said there, the function containing the variable x. If it was f of t, then I would have a little power of t up in the corner. And that's kind of a brief overview of Unit 6, which was on exponential functions.